Hey mathematicians, let's go ahead and have a look at some problems with non-vertical asymptotes. All right, so what are we talking about here? Easiest thing to do is just do it by example. So let's have a look at the following function. Okay, suppose y is equal to x plus 2 squared, x minus 2 over x minus 1 squared. Okay, so a couple things that I want us to be aware of. If we look at sort of overall what the gist of this is kind of like an x squared times an x over an x squared. And so the shape of this is going to have an x squared cancel out an x squared. This is kind of like a y equals x graph, which means we should expect the horizontal asymptote to really be a diagonal or slant asymptote. It should look kind of like y equals x, or y equals x plus 3, or y equals x minus 7, some kind of diagonal line. Now, just what is that diagonal line? That will require a little more analysis, and that's sort of the point of today. But the overall gist of this graph is going to be an x, like a y equals x kind of a thing. All right, let's start getting specific. We'll check step 1. All right, so 1, we're going to ask, are there any holes? All right, remember, holes will happen when the numerator and denominator have the same factor. Here we have none to worry about. Okay, step 2, we're going to ask, when do we have vertical asymptotes? Okay, the vertical asymptotes happen when the denominator equals 0. Okay, the denominator equals 0 happens when x is equal to 1. So let me just, I'm going to just recopy this problem a little lower, and it'll be a little easier to do the analysis on it. All right, so I can drop it off screen. Okay, so the denominator, so I'll just sort of draw some sort of set of axes. When x is equal to 1, we have our vertical asymptote. Okay. What else do we have? We had the denominator equal to 0, so now let's make the numerator equal to 0. The numerator equals 0 gives us x-intercepts. Okay. Our numerator is equal to 0 at positive 2 and at negative 2. So those are the places where the numerator equals 0, positive 2 and negative 2. All right, and then let's see where they're going to look at when x equals 0. When x equals 0, we're going to have our y-intercepts. Okay, so our y-intercept when x equals 0, when x is equal to 0, so I'll do a little bit of work over here on the side. I get 2 squared times negative 2 over negative 1 squared, which is overall some value of 8. Ugh, that's going to be a big number. 1, 2, 3, 4, 5, 6, 7. All right, so it's going to be some positive number. It's big, and I will run off the edge of my picture. So I'll just sort of draw it here. So some fairly large positive y value. I'm going to just sort of move my writing over here on the side. Step 5 is going to be our horizontal asymptote. But it's not anymore a horizontal asymptote. We know this is going to be a y equals x cubed over x squared, which is like a y equals x. So this is really going to be our non-vertical asymptote. Okay, let x go to positive or negative infinity. Now here, if I let x go to positive or negative infinity, I get x equals y equals x. So that's going to go to positive infinity on this side and negative infinity on that side. So we're actually going to have to do a little more analysis on it. And the way we're going to do that is to do some algebra. What do we mean by that? I'm going to rewrite the equation one more time. Y equals x plus 2 squared times x minus 2 over x minus 1 squared. What we're going to do is we're going to actually do some calculations Let me just write this out twice so I can do some foiling. So I have to multiply x plus 2 times x plus 2 times x minus 2. And the way I'm going to do that is to do this difference of squares first. It'll just make the numbers that I deal with a little easier. Okay, the denominator is just a perfect square trinomial. The numerator ends up being an x cubed. That's my x cubed. Then I'm going to have plus 2x, and then minus 4x, and then minus 8. That's my numerator. My denominator, x squared minus 2x plus 1. All right. So what do we have here? We have basically the original problem, but now I've written it in polynomial form, sort of standard polynomial form. And that right now, as it is, doesn't do us any good. So what are we going to have to do? We're going to have to do some long division. I know that's going to be one of your favorite things, so we're going to revel in it while we can. X cubed plus 2x squared. Oops, sorry, there should be an x squared. Minus 4x minus 8. And we're going to do some long division. X squared times what equals x cubed? X squared times x. So then I'll take that x times x squared is x cubed. X times 2x is 2x squared, but it's negative. X times 1 is x, and that's positive. So I multiply. Now I'm going to subtract that. X cubed minus x squared. X cubed minus x cubed, 0. 2x squared minus negative 2 gives us 4x squared. Negative 4x minus x is negative 5x. And then I'm going to bring down a negative 8. Okay, what does that do for us? Now x squared times what gives me 4x squared? I'm just going to change colors here. X squared times 4. So I'm going to do plus 4. 4 times x squared is 4x squared. 4 times, excuse me, 4 times negative 2x is negative 8x. 4 times 1 is 4. And then we'll subtract that. 4x squared minus 4x squared is nothing. Negative 5x minus negative 8 is negative 5x plus 8x is 3x. Negative 8 minus 4 minus 12. Okay, so now what does that do for us? That tells us that our equation, our original y is equal to this thing squared over the squared, is really the same as y equals x plus 4 plus 3x minus 12 over x minus 1 squared. Okay, so that's our remainder. Here's our quotient. What does that tell us? That tells us that this function, the original f of x, wants to be y equals x plus 4. It wants to be y equals x plus 4. It's not quite y equals x plus 4. It wants to be. I mean, it's off by a little bit by this remainder. But this y equals x plus 4, that's our non-vertical asymptote. Okay. So our non-vertical asymptote is the quotient. It's the result of that division problem. And now what's going on with this remainder? Well, let's first make a sketch of that asymptote. Y equals x plus 4. So it's got a, we have a 1, 2, 3, 4, 1, 2, 3, 4. So this is really going to be at 8. So I'm going to just draw this a little bit lower. I'm going to leave this at 4 here. So I have this diagonal line. This is the line y equals x plus 4. The horizontal, like a y-intercept of 4, and then a slope of 1. If I were really trying to be careful, this dot would have been up a little higher. But the idea here is that this is where my graph is headed towards. Okay. The other thing that the other thing that I want to make clear is that I have the remainder right here. Now this remainder is telling me that I'm not quite equal to the asymptote. But there is one place where my function actually equals the asymptote. And that's when the remainder is equal to 0. When the remainder equals 0, then the graph touches the non-vertical asymptote. What's going on with that? It's touching the non-vertical asymptote because if the remainder is 0, then it's just, f of x is just x plus 4. So this remainder is 0 when? When is the remainder 0? When 3x minus 12 equals 0, or when 3x equals 12, or when x equals 4. So what is that saying? It says our graph at 1, 2, 3, 4 is going to actually touch our asymptote. It's gonna equal our asymptote. All right, let's see if we can figure out some information about our graph now. And no wonder everything was messed up. Of course, the y-intercept should be a -8, not +8. Duh. Okay, y-intercept is 8, is -8. -8, not +8. Okay, sorry about that, guys. All right, that's what happens when you're not paying attention. -2 for me, and now when I look at this graph, it starts to make sense. Okay, we could do some sign analysis, but you guys know we don't actually have to do sign analysis because we've kind of got all the signs we need. What do I mean by that? Our sign analysis would tell us that we're negative over here, clearly. We're positive over here. Do we have any double roots? Oh, we got double roots a lot. X plus 2, so this is a double root right here. So if it was negative, it's going to stay negative, and we knew that already. It's going to be negative down here. Negative turns to positive over here. Oh no, that's a double root also. So this is a double root, which means it's going to, if it's negative, it's going to stay negative. Would that sort of make sense? And then we're going to end up positive out here. All right, so what are we looking at? Final graph is going to look something kind of like what? It's going to bounce off here. It's going to be like the asymptote. It's going to bounce off here, go to negative infinity, and then that's our double root that's bouncing. Here our double root is a little Atari or volcano, so that's going to also go down. This is going to come up positive. It's going to skim towards the asymptote, but we know it actually crosses the asymptote there, so it must be a little bit above the asymptote. And that's what this thing looks like. Isn't that awesome? I'm just going to sort of follow the asymptote like that. Okay, this is a little whacked out, a little crazy, but that's pretty awesome, isn't it? All right, I'm going to stop here, and we'll just try another example in the next video.